Hello, I'm Craig Prunty, VP of Marketing for SiPearl. I'm happy to be with you here at the ISC 2021 AHUG workshop. SiPearl was founded in 2019 to bring to market the high-performance European processor. We're a fabless CPU design company with HPC as our target market. Seed money through the Horizon 2020, and we're currently in Series A funding activities. Our first employee started in January 2020, and we're now at 35 employees and are aggressively hiring for our design centers in France, Germany, and more recently in Barcelona, Spain. We're well into the design of our first generation processor, Rhea. The Rhea architecture is based on the Arm Neoverse V1 core, which incorporates in-package HBM for memory bandwidth performance and leverages the Arm Scalable Vector Extension instruction set. There are four pillars to the SiPearl value proposition: a high-performance ARM server processor, a common platform to join Rhea with accelerators, safety, security and data protection, and sovereignty to develop the EU digital ecosystem. Our first processor, Rhea, is an HPC dedicated CPU including ARM SVE, high bandwidth memory, and a focus on a secure and fully auditable solution. We chose the Arm Neoverse family for the performance of the cores and SoC elements, but also importantly for the ARM server processor ecosystem. EU sovereignty is equally important for SiPearl. As the European processor solution, we want to grow the European ecosystem and value chain, ensuring that the European-funded projects can benefit from and generate new European technology, such as acceleration, security, and tools. The flexible common platform is a good example of this, where SiPearl will work with European partners in a platform approach to closely couple acceleration with our general purpose processors. Finally, safety, security, and data protection are key European values. HPC markets have fairly basic security needs such as secure boot, upgrade, and storage. But cloud and edge markets security requirements are continuing to evolve, and we will focus our innovations there. SiPearl's first market is high-performance computing, focusing on delivering for Exascale systems. Our lead customers are European HPC centers. We develop products based on European customer needs and then market to the rest of the world. HPC market growth is accelerating due to the race to exascale, the proliferation of AI, and the fast adoption of HPC in the cloud, which according to Hyperion has a 5-year CAGR of 25%. The European cloud market, including central and edge data centers, is also growing, and the European Commission is pushing forward sovereign initiatives like Gaia-X and IPCEI. European edge use cases will range from 5G and smart cities to industrial edge and automotive. We will right-size our cloud processing performance for the appropriate market while innovating and supporting advanced security features. Arm is an important SiPearl design partner, delivering their Neoverse solutions with their POP IP architecture. There is also the advantage of the Arm ecosystem, from tool chains and library support to driving customer awareness and education. Arm has a huge and growing presence worldwide with nearly 200 billion processors sold. Focusing more specifically on the server market, there has been an incredible growth in the last 5 years across Europe, North America, China, and Japan. Riken Fugaku supercomputer has topped the HPC lists this year. The European Mont Blanc and CEA systems, the UK Isambard and Catalyst, the US Sandia and Stony Brook ARM systems, as well as other research systems, show that the ecosystem is driving new HPC business across the world. Other key partnerships are the EPI. For SiPearl, this offers a wealth of design partners, customers, and IP providers for the development and distribution of Rhea. The main EPI objective is to develop a complete EU-designed high-end microprocessor addressing supercomputing and edge HPC segments. A key element in our choice of the ARM ISA is the server and HPC ecosystem, the elements that go into the system and system development. This representative list of partners shows the amount of time and investment put into the ARM ecosystem development and continuous upgrade. If we consider Calxeda, founded in 2008 to be the first ARM server processor company, the ARM server ecosystem has been at least 12 years in development. It is now robust and growing independently with user groups, commercial companies, hackathons, and consortiums all contributing. This slide shows processing trends over the last few decades. At the turn of the century, the majority of architectures were single core, with performance gains coming from architecture and core microarchitecture decisions, but largely driven by core processor frequency. As frequency gains slowed, architectures parallelized and moved to multi-core designs for performance improvements. For roughly a decade, the growth of processor performance was driven by increasing core counts. When power became a limiting factor, there was a further move to heterogeneous many-core designs, using acceleration to boost performance beyond what general-purpose processors could support in an equivalent power envelope. In HPC, this included GPU and accelerators like the Intel Xeon Phi, and today you have roughly 30% of the top 500 supercomputers, mostly at the top end of the performance scale, using accelerator or coprocessor technology. At each wall, there's a natural resistance based on the ecosystem and software changes required to implement and maximize performance on the new architecture. Looking forward, we see the end of the current compute decade as a cost wall due to the slowing of Moore's law and the increasing cost of lower geometry fabrication processes. This heterogeneous many-core decade is marked by the race to exascale computing. Other trends driving growth are the proliferation of AI, and more recently, the trend from global outsourcing to the investment in sovereign core competency. Now let's look at the trends in HPC to take us beyond the cost wall. A natural evolution we see in European exascale systems is a focus on a modular system approach. This block diagram is from the Unisys Supercomputing Center in Germany. The cluster module, or CPU module, supports the broad range of user workloads without requiring lengthy software porting and optimization. The booster module incorporates GPU for both floating point performance and AI training. This architecture can also easily incorporate other modules such as neuromorphic and quantum computing to further research in these domains, which are likely to break the next wall in processing architecture evolution. The value of this design is that each module can be independently scaled and upgraded, supporting a wide variety of workloads. The challenge for this type of system is the increased software and maintenance requirements for supporting the different modules, though this can be simplified by keeping a common CPU across all the modules. Here I'm going to show a bit of information about the SiPearl Rhea processor, our first generation processor. There's a lot I can't share without NDA, but we've chosen the ARM V1 core for its excellent floating point performance and intelligent memory subsystem. The choice of the ARM ISA is driven by performance, energy efficiency, ARM's IP, and the server software ecosystem. The memory coherent NOC is topology aware for design scalability and flexibility, scaling designs to fit multiple markets. With this architecture, we benefit from good computing element isolation while supporting coherent SMP across chip domains. Our memory subsystem includes both HBM and DDR linked to a generous shared last level cache. High-speed I/O includes C6 and PCI links to NICs and accelerators. The ARM V1 core, in addition to its good general-purpose compute performance, includes 2x256 SVE engines. This gives a tremendous performance boost at low software overhead as the compiler generates vectorizable code for the SVE engines. Generally speaking, the closer the offload is to the processor core, the lower the software burden. ARM SVE engines support double precision, single precision, bfloat 16, and integer 8 workloads for vector processing or AI and machine learning. The choice of 256-bit vectors gives us the best trade-off of performance versus power or area for a number of reasons. First, we estimate our average customer vector size is between 256-bit and 512-bit, generally speaking in the 300-bit range. So 256-bit gives us the best performance across our customer's average vector size. As a CPU, we target HPCG efficiency across all workloads instead of LinPack performance on a limited number of workloads. The choice of 256-bit vectors drive efficient performance per watt and performance per area in terms of chip sizing and chip power consumption. And because it's a CPU, this is supported across all workloads. In conjunction with HBM, SVE gives great performance and a high byte per flop ratio. Overall, the 256-bit vectors provide the best trade-off across the targeted HPC workloads and AI and machine learning. By definition, Exascale requires high floating point performance. Sustained 10 teraflop per node would require 100K nodes to meet Exascale, which is a large but manageable system size. We see systems larger than this, such as the Fugaku supercomputer, but these systems tend to be built with processors specifically architected for the intended system, often to the detriment for use in a wider scale. The graph on the left is another way of viewing the modular architecture. As discussed previously, most exascale systems will use acceleration, and typically this means GPUs. GPUs are useful for LinPack scores but support a limited number of workloads, and the software model is complex to implement and difficult to migrate. The flexibility of CPUs make them the workhorses across all required workloads. This requires a balanced processor with high memory bandwidth to deliver the data and processing performance to crunch it. HBM plus native acceleration for processing power with the appropriate memory bandwidth. In the chart, you see increasing flops along the x-axis. This is serviced by GPUs, with the CPU providing a balanced performance measured as bytes per flop. The interesting part of this graph is the white space that dominates the center, which grows in relative size as we race to exascale. The white space emphasizes the modular architecture with different nodes providing different capabilities along the two axes. Byte per flop is an important KPI as a measure of the CPU portion of the system, since this is the module that will support all workloads. However, byte per flop is insufficient by itself, as you can drive the byte per flop up by driving flops to 0. Gigaflops per watt is an important KPI, but taken by itself, it encourages designs that target specialized accelerators and software optimized for LinPack at the expense of the majority of workloads. An important HPC metric is HPCG efficiency, which captures both memory bandwidth and floating point processing requirements. This is seen in the graphic on the right as the ratio of HPCG over R peak as a percentage of effective system processing. The white space above the HPCG waterline up to R max represents system resources that are not optimized. Since systems that focus mainly on high flops performance typically do poorly in this measurement. These three KPI, byte per flop, performance per watt, and HPCG efficiency, in addition to co-design with partners in the EPI, are driving our Rhea architecture development. It's been my pleasure to present an overview of SiPearl, the Rhea processor, and the EPI common platform. You can contact me or SiPearl with the information listed above. Have a great ISC 2021. Thank you.